Welcome to Data Science 1, Probability, Expectation. So, items to remember, you're going to need to know what the binomial distribution is, and you're going to need to be really familiar with it because I'm going to use it, and I'm not even going to show you where I use it. So you're going to have to be able to calculate these on your own, as we've done in previous videos. All right, so here's the idea of expectation, and it's quite general. It's like the mean, but it's quite general in the sense of we have a function g of x that's defined on the same domain as the probability distribution function. The expectation of g of x is defined to be, and we're going to write this with e brackets, and then we're going to put g of x in there, is the sum of g of x times f of x. And this is, e is what's called the expectation operator. Now, this looks a little complicated, but it isn't as complicated as you would think. It simply weights each of the values in the outcome of g of x based on how likely you are to see the value of x. So if the value is likely, then seeing g of x is likely. So we would just multiply those together. And we've already seen this when you've played around with the mean. So if I look at this, here we have mu is the expectation of the expected value of x. And if I stare at this long enough, I can see that here is g of x. G of x is equal to little x. And the mean of the value of x is more likely, or the values of x that are more likely get more weight, and the ones that are not likely won't get much weight. Now, it is a weighted average, and a lot of you have created weighted averages before, and you've subjectively come up with some weights. Here, the weights aren't subjective. The probability distribution defines them. Hence, they're not up for negotiation. I've had this discussion with people before. They've said, hey, well, what if we change the probabilities to be this, this, or this? I said, that's not how this works. Probability, the experiment, that defines the probabilities. So you can't really mess around with them. All right, so let's look at this more general example of expectation. I'm going to try to use an example to illustrate it. So suppose I'm testing a new biodiesel fuel for trucks. I have 5 trucks to use for my test. The outcome is simple. If the engine starts using the new fuel and runs for 1 minute, it's considered a success. Otherwise, it's considered a failure. Due to the type of fuel, there is a repair cost associated with each failure. To modify the engine to accept the new fuel costs $35, or not dollars, euros, which is the same cost for all 5 trucks. This has to be done to all 5 trucks in order to run this new fuel. However, for each failure, there's an additional cost of 85 euros to clean the fuel system to accommodate the old fuel again. So we need to take the stuff we put on there off and clean everything up so that it will work. So what I'm interested in here is my expected cost of the experiment if the probability of failure is 0.3 for each of the n equals 5 trucks. Now, notice here I said probability of failure. So I'm going to flip this over, and my success is going to be failure in this case, with p equals to 0.3, and here n equals to 5 trucks. So the first thing I need to do is come up with g of x. So x is going to be the number of failures across the 5 trucks. So let's see. Well, there's a sunk cost. All trucks have to get the 35 euro adaptation. So that corresponds to 175 euros for the fuel apparatus installation. Now, each failure will cost us 85 euros. Hence, we have g of x here equals to 175 plus 85 times x, where x is the number of times I have to take apart the old stuff and put in or take apart the new stuff to put in the old stuff. All right. So here is a table. I just made out a table of it, how to calculate everything. So here my x values, 0, 1, 2, 3, 4, 5. Those are my only options because I only have 5 trucks. Okay, so here I'm just going to plug in 0 over here for x. So I've got 175 plus 0 times 85 equals 175. Okay, there was no failures, so it only cost me the 175 euros. Here, if I had one failure, I have to account for that 85 euros. So now it becomes 260. If I had two failures, now I have to account for two sort of rebuilds, which is 345 euros. And here are the others calculated out. Now here is the binomial distribution, and it's calculated out for you. So you would have to go in and plug in here n equals 5, x equals 0, with p equals to 0.3, and you'll get these numbers here listed. You just have to change the x as you go through it. Okay, so to get g of x times f of x, we take the g of x number. This is the value, the cost it's going to cost us if there are no failures. And then here times the probability of no failures. And that would give me 29.40 euros. Again, one failure would cost me 260 euros times the probability that that would occur, which is 0.360. So that would be the values multiplied together is 93.6. And so on all the way down. You would do this computation all the way down. I didn't show all the details, but here are the numbers. You should go through and work them out for yourself. And you can see that the probabilities total up to 1, which they should because it's a probability distribution. If they don't, you should be worried. All right, now over here is the actual expected value, right? Because we've summed them up now. We've summed up g of x times f of x, and we've arrived at 302.59 euros. Okay, so the expected value of my experiment is around 302 euros. We'll just say that. Now, notice this is very different way of thinking. The way of thinking is, what's the worst case scenario? Well, that would be 600 euros, right? Because the 600. But look how unlikely that is, right? Or you could say, well, what's the most likely thing to happen, which would be this 0.360, and that would be 260 euros. So this lands us somewhere in between there, and it lands us much closer to a reasonable value of what we would think the expected cost would be. All right, so expectation is a really big idea in statistics. So it's useful for decision making. It's useful for determining various quantities of interest, as we'll see soon. Incorporates probability into our weighting scheme. Now, expectations have lots of properties, and we'll cover those after we cover continuous distributions, which will be a couple videos away. But right now, I want you to know that this is just the basic idea. I'm going to cover it again with continuous distributions. And what we'll see is that the properties that are from this make lots of other things really useful, and we'll talk about that as well. So we'll see you in the next video.